This is Chapter 7, where we're going to be working on applications of trigonometry. We're going to be solving oblique triangles in the first 3 sections, and then the last 2 sections are on vectors. Section 7.1 is on oblique triangles and the law of sines. Let's review a little bit of geometry. So congruence axioms. Suppose that you are given a triangle and we know the length of 2 sides and an included angle. So let me draw a picture of this. If we know the lengths of 2 sides and an included angle, if there's another triangle that has the same 2 lengths and same angle, those 2 triangles are congruent to each other. The second one, if we're given a triangle that has 2 angles and an included side of one triangle, so suppose that we're given 2 angles and then the included side. If you have another triangle that has the same measures of those 2 angles and the same length of the side, then those 2 triangles are congruent to each other. And then the third one, if you have 3 sides of one triangle, and there's another triangle that has the same lengths of the sides, then those 2 triangles are congruent. A triangle that is not a right triangle is called an oblique triangle. A triangle can be solved, that is, the measures of the 3 sides and 3 angles of a triangle can be found if at least one side and any other 2 measures are known. We've already solved right triangles. We did that back in Chapter 2. Now we're going to work with oblique triangles. These are triangles that are not right. As long as you know the length of one side and any other 2 measures, they could be angles or sides, then you could solve the triangle. You could find all the other unknown lengths. Data required for solving oblique triangles. We have 4 cases. Case 1 is if we're given one side and 2 angles. Either that's the SAA case or the ASA. And if you look back over here, we have the ASA case, and that's drawn there. Let me draw a picture of the SAA. That's where you're given 2 angles, and then the side that's given is not between them. The second one, where the ASA, is where the side given is between those 2 angles. Case 2 is where we're given 2 sides and 1 angle that's not included between the 2 sides. This is the SSA case, and this may lead to more than one triangle. This is where we're given 2 sides and an angle that's not between them, so that would be something like this. Case 3 is when we're given 2 sides and the angle included between them. And this is the SAS case. We already saw that up here, where you have 2 sides and the angle between them. Case 4 is when 3 sides are known, and this is called the SSS case. We're going to look at case 1. We're going to look at case 1 in section 7.1. Case 2 is 7.2. Case 3 and 4 are both in section 7.3. And then here, if we know 3 angles of a triangle, we cannot find a unique side lengths because this AAA case only assures us of similarity and not congruence. You could have 2 triangles that have the same angles, but one could be larger than the other. These triangles are similar, but not congruent to each other. All the angles are the same, but not the sides. Let's go on to the next page on a derivation of the law of sines. To derive the law of sines, we start with an oblique triangle. Either we could have an acute triangle, and that's this one here shown on the left, or an obtuse triangle that's shown on the right. Either way, both of these will work when we're going through the derivation. We're coming up with a law of sines, which we're going to use to solve triangles later on. This discussion applies to both triangles. First, construct the perpendicular from B to side AC. So you see how that is the height of the triangle, so that's H. Let H be the length of this perpendicular. Then, if we look at triangle ADB, so that's ADB, do you see how C is the hypotenuse of it? And that's in both triangles. And A is the hypotenuse of the right triangle BDC. In triangle ADB, sine of A, here we have angle A, so that would be opposite over hypotenuse, so that's H over C. And if we solve this for H, we'll have H is equal to C sine of A. In triangle BDC, sine of angle C, it's opposite over hypotenuse, so that's H over A. We solve for H. H is equal to A sine of C. Because H is equal to C sine of A and A sine of C, we can set these two expressions equal to each other. So that means A sine of C is equal to C sine of A. Remember, the lowercase letters describe the lengths of the sides and the uppercase describe the measures of the angles. And then I'm going to rewrite this. And we're going to divide each side by sine A sine C. And if we do that, do you see how the sine C's will divide out? The sine A's divide out here. And we have A sine over sine of A equals C over sine of C. And in a similar way, we could come up with these other two formulas. This is called the law of sines for any triangle ABC. With sides A, B, and C, all of these are true. Or we could just set them all equal to each other. That is, according to the law of sines, the lengths of the sides of a triangle are proportional to the sines of the measures of the angles opposite them. Let's write that all out in another way. If we go up to the top of 7.3, an alternative form of the law of sines is we can just write the sine in the numerator instead of in the denominator. So sine of A over A is equal to sine of angle B over side B. That's equal to sine of C over C. You're going to do some examples, and then let's go over to page 5, so 7-5, and look at the area of a triangle. For the formula for the area of a triangle, we can use this formula when we're given the SAS case. If you're given two sides and an angle between them, then you can use one of these formulas. And do you remember the formula for finding the area of a right triangle is 1/2 times base times height? Well, remember that we were able to find the height when we had base B. One of the heights was C sine A. And so you can see that's where this formula here comes from. And then if you twist it around using different heights, depending on which way the triangle is going, then you can come up with those formulas. That is, the area is half the product of the lengths of two sides and the sine of the angle included between them.